Hello and welcome back. I'm Will Reynolds at the University of Edinburgh, and in this video I'm going to explain how to sort a stack of pancakes using only a spatula. If you haven't seen my previous video, then that sentence probably sounded quite strange, and you should definitely go and watch that video before watching this video. I should emphasize that there is scope for multiple solutions to this puzzle. The solution I'm going to present is probably the simplest, but in fact the puzzle is essentially the entry point into a whole area of research of its own. So do check out the Wikipedia page on pancake sorting after this video. Okay, so after playing around with some examples, and I do recommend playing around with small cases here, it's very helpful, I made the following observations. First of all, after at most 2 flips, the biggest pancake can be put at the bottom of the stack. And also, the spatula, the way the spatula works, it doesn't affect anything below it. So why is that important? It's important because it means that once we've got the biggest pancake at the bottom, we can just ignore it. We can pretend it isn't even there. And then we're no longer dealing with a stack of size n, we're now dealing with a stack of size n minus 1. Let's see this in action with an example. So here's an example with a stack of size 4. Over on the left-hand side, I've got a stack of size 4. And you can see the biggest pancake here is second from the top. With one flip of the spatula, I can move that to the top of the stack. I just put the spatula in here. And I flip over these two, and that goes to the top. Then I use the spatula to flip the entire stack over, and the biggest pancake winds up on the bottom. Now I do the same thing with this stack of 3 pancakes. So now the new biggest pancake, because I'm ignoring this guy, the new biggest pancake is again second from the top in this case. I flip that to the top, then I flip over this little stack of 3 pancakes, and that goes to the bottom of the stack of 3, and so forth. And the point is, if I continue this way, then we should end up sorting the entire thing. And then the thing to notice is in these middle 2 steps, in fact, from this point onwards, I ignored the biggest pancake in the stack of size 4. I didn't need to pay any attention to it. Here's a description of the algorithm written out in more or less plain English. So the input is a pancake stack of size n, which we'll call S. The output is the sorted pancake stack of size n. First things first, if the S that you're given, if the stack that you're given is already sorted to begin with, then you don't need to do anything. Just return S. On the other hand, if you reach this point in the algorithm, then your stack is not already sorted, so you have to do something. So let B be the biggest pancake. I don't want to repeat myself all the time. So if B is not at the top or the bottom, then move B to the top in 1 flip. And if B is at the top, then move B to the bottom in 1 flip. So these 2 lines ensure that our biggest pancake B winds up at the bottom in at most 2 flips. And then I repeat this on the substack of top n minus 1 pancakes. I think it's quite believable that this algorithm is going to work. At least if you try it on some examples, you'll see. But let's examine the underlying logic here, just to be sure. The algorithm obviously works if n is very small. And by works, I mean will always work, no matter which stack of size n you give me. Why do I say this is obviously true? Well, because if you have a stack of size 1, then you can just try the algorithm. If you have a stack of size 2, then there's only 2 possibilities for a stack of size 2. Just try the algorithm on all of them. You can see that it works. Now, if the algorithm works for every stack of a size n, then it also works for every stack of size n plus 1. So if you give me any stack of size n plus 1, after at most 2 flips, I've now reduced that down to a stack of size n. And I just said, if the algorithm works for every stack of size n. So I'm assuming this. So once I've reduced it down to a stack of size n, then I know it's going to work. Hence, the algorithm works for every n, right? Once you know it works for n equals 1 and n equals 2, then the second bullet point means it also has to work for n equals 3 and n equals 4, and n equals 5, and so forth. This kind of reasoning is called mathematical induction. If you haven't heard of mathematical induction before, that's totally fine. We teach it to first years in PPS, proofs and problem solving. The main part of the puzzle, however, was to analyze the algorithm you come up with to see how it performs in the worst case scenario. So that's what I'm going to move on to now. I have to start somewhere, so let's define a function w of n. Let w of n be the largest number of flips required for this algorithm to sort a stack of size n. The first thing to notice is that the way the algorithm works implies a certain inequality, which I've written down here. W of n is less than or equal to 2 plus w of n minus 1. Right? The worst case scenario, or a worst case scenario, for a stack of size n can't be any worse than 2 plus a worst case scenario for a stack of size n minus 1. That's because the algorithm reduces a stack of size n down to a stack of size n minus 1. For any stack of size n, which requires w of n flips, so for any worst case scenario stack of size n, I can then make a stack of size n plus 1, which requires exactly 2 more flips. Here's how that works. Give me a stack of size 2, which is a worst case scenario for 2. There's only 1. I flip over this stack, and then I insert the new largest pancake second from top. This will take 2 flips to reduce back to this stack of pancakes. 2 flips to put this pancake on the bottom, and then I'm back to this guy. Then I just repeat the process. Flip this guy over, flip this stack of 3 pancakes over, and then insert a new largest pancake second from the top. This will take the algorithm run on this will take 2 flips to put the new largest pancake at the bottom, and then you can see that the way I've constructed this, the stack of 3 pancakes on top is now going to be this stack of 3 pancakes, and so on. So what's the point of this sequence of examples? Take any stack of size n minus 1, which requires w of n minus 1 flips, so any worst case scenario for n minus 1 pancakes. Do as I said. The new stack requires exactly 2 more flips. Therefore, the worst case scenario for a stack of size n has to take at least this many flips, because I produced a stack of size n which does take this many flips. So the worst case scenario has to be at least as bad as this, or worse. So now we're almost done. For every n bigger than or equal to 2, we've shown that w of n is both at least 2 plus w of n minus 1, and at most 2 plus w of n minus 1. At least because of the sequence of examples constructed, and at most simply because of the way that the algorithm works. But now, clearly this means that w of n has to equal 2 plus w of n minus 1 for every n bigger than or equal to 2. Now, since w of 2 equals 1, and w of n equals 2 plus w of n minus 1, we get a formula. This is a simple arithmetic progression, and we know what the first term is. So w of n is equal to 2n minus 3 for every n bigger than or equal to 2. So that solves the problem. That means that this algorithm, in the worst case, takes 2n minus 3 flips to sort a stack of size n. I really hope you enjoyed this puzzle as much as I did. If you came up with your own solution, a different solution, then why not share it in the comments? Remember to like this video and do check out the other videos made by my colleagues. They asked some great questions as well. Good luck with all of your future studies, and thanks for watching.